right, hello everyone. Let's get ready for the lightning talk session. So, we do this first come, first serve. If you would like to speak, please line up here on the left-hand side so that we don't block any of the exits. The rules are fairly simple. You get the mic for 3 minutes. Bring your slides if you want. If you don't have any slides, that's also fine. There's a USB-C and HDMI here. That should work. I'll be sitting down and enjoying the talks with a timer. If the timer of 3 minutes expires, I'll give you like a sign like this. It's time to wrap up. If you don't wrap up, I'll have this very obnoxious device to enforce the timeline. And yeah, I think that's it. Let's get started with Siamak.
Thank you, Joachim. So I just want to take a couple of moments here. Is this working? To just make an announcement. It's great to have SBC here in New York City this year. I think that's kind of an acknowledgement that New York has really become a central locus for blockchain activity, both in academia and in practice. And so given that, I want to invite everyone here back to New York City and to Columbia in December, when we'll be hosting the 3rd annual Columbia Crypto Economics Workshop. Our goal in organizing this for the past 2 years has been to try to be the premier event, bringing together academics and practitioners to discuss issues related to economic incentives in blockchain. So here we're thinking of topics like transaction fee mechanisms, MEV, restaking, roll-up economics, and so forth. It's an event that's co-organized between members of the Robust Incentives Group at the Ethereum Foundation, myself at Columbia Business School, and my colleague Tim Roughgarden in the School of Engineering. And given that we really try to have, like SBC, kind of both the top researchers in academia and in industry, and try to carefully curate that. And so, you know, we're going to have more information about the event coming in the upcoming months. But for now, just remember the dates, December 4th and December 5th. There's an URL there where you can see what we did last year and where we will also post new information. And we hope to see you in December. Thank you.
So, speaking of events, okay, okay. If you'll be, well,
Try again.
sure. What? Sure thing. Here we go. What? It's and it's not working. It's always a fun thing at conferences, a room of smartest people ever. The slideshow never works, nothing ever works. But we can do this. I trust in us. Anybody on the technical team? Smear display. Let's try it here. Yes.
You don't have a bongo, right? You don't have a thing?
It's doing something.
It is doing something. Windows. God, you don't have your file, right?
What?
You have the file?
I can send you a link for this.
It's gonna take forever.
A link?
Yeah. You want to send?
It's just, oh,
Put the next
Yeah.
person. Put the next person.
okay, yeah.
Hey everybody, my name is Vanashri. I have a couple of research questions, the solutions to which I think will be helpful for the ZK industry in general. One question is around trusted setups. Currently, what is happening is that different projects with different proof systems need to do their own trusted setups, which is operationally expensive and time-consuming, in general resource-consuming. The question is, is it possible to do one single truly universal trusted setup that different projects across the industry using different proof systems can utilize? And here is a starting point to think through a solution. I think the reason why different trusted setups are needed is because the way we have on-chain verification is by having one hop away from the proof system by using Groth16. And the Groth16 prover proves computation of the verifier, which of course is variable because you're working with different proof systems. Instead, how about the following direction? If you put something like a flonk in between, so you start with your proof system, then prove its verification using flonk, and then you go to Groth16. Here, this is a starting point. This still does not work. Why this is a starting point is because you want to, the goal is, I think, a solution for this, the goal is to find an endpoint of proof system where the prover only does some generic computations, and the only variant has to be the size. And you can do that by, I think, a few hops. I think one hop. It's okay, I'll talk through it. One hop doesn't work because here, the verifier of flonk also, it seems that it is it's dependent on the computation that its prover does, so it still does not work. I think, and the idea could be that goes so succinct that the prover of the final proof system can do everything in just addition and multiplication, and then it's just the size. Okay, I think my time is up. There is one more nice problem, but if anyone is interested in collaborating, please come talk to me. And by the way, one last sentence, we are building FIRMA, a universal proof generation layer. Thank you. Come talk to me if you're in ZK space, please. Thanks.
All right, let's see if this works with my laptop. No mechanism of predicting these things in advance. Okay, well, that's a good sign. And it's gone. Yeah, I just would like it to not mirror if at all possible, but this seems too hard to figure out right now. Anyway, I'm Isaac. I work for Heliax on Enoma. I'm a scientist, and I want to talk about technologies for cross-chain atomic commits. So these will eventually make their way into the Typhon project, which is for building Enoma native chains within the Enoma software ecosystem. So I want to start with the train and hotel problem. So this is the problem where I want to book a train, presumably on one chain, and a hotel, presumably on another chain, and I don't want to book neither. So I want these to be booked atomically. A traditional way to do this would be with a multi-phase commit. So we start out by locking resources on each chain. until they're both locked. There's some interchain communication, and then we do an unlock phase where we commit or abort. There are 3 problems with this. One of the problems is liveness. If we lock our resources on one chain and the other chain dies, then we're just screwed. We've somehow set the liveness of all the resources to the worst of all the chains involved. Another is that it takes multiple rounds. Anything that does this requires at least 2 commitments, at least 1 round of interchain communication. There's a certain inherent slowness. And finally, there's a kind of free option. Whichever chain communicates last has the ability to decide exactly when this transaction happens, which might be valuable, and that in turn might be a problem. We don't want to incentivize chains to delay stuff. So ideally, the thing that these chains are doing, I mean, they're already running consensus. They're already doing atomic groups of transactions called blocks. What we're trying to simulate fundamentally is putting one block on 2 chains, one group of transactions atomically committed to both. So let's try and make the easy case easy. This is based on a consensus algorithm I published in 2020 called heterogeneous Paxos. And the easy case is derived from looking at the actual quorums that do the consensus of these chains. I'm assuming we're doing something with finality. So let's say the quorums for red chain look like this. Obviously, they would have to intersect. The quorums for blue chain look like this. And the easy case is when all the quorums of one chain intersect all the quorums of the other. A decision made by red will have to be respected by a decision made by blue as long as each of those red-blue quorum intersections contains an honest validator. And this may sound like an unusual case, but it's actually not that uncommon. Proof-of-stake chains tend to have a fairly large amount of validator overlap, in part because they're just professional validators who make a business out of doing this, and they do it for a lot of chains. So it turns out that there actually are cases when it's possible to have, for example, a red-blue commitment and a blue-green commitment, but there isn't enough overlap to do a red-green commitment. So our proposed answer to this scenario are what we call chimera chains. It's a chain for each possible heterogeneous consensus, and they are sort of a separate place for doing these red-blue transactions. I don't have time to go into a lot of details about how the programming model for these works, but it does require explicit support from the base chains, and we hope to integrate that into future ANOMA chains. Thank you.
Okay, attempt number 2, we have the slides. It must be easier. Okay, so we're going back a bit to event things. I'm Clara Schickelman. I'm with Chaincode Labs. We're a nonprofit here in Midtown Manhattan focused on Bitcoin research. And we have a bunch of cool things coming up in November. So the Bitcoin Research Day is going to be the 2nd edition of the previous event. It was really good. It's going to be even better this year. Some of the speakers are present. Go to the website, see it. We're going to get core developers, engineers, academics talking to each other, doing some very cool stuff. Some of the other cool things that are going to happen at the Bitcoin Research event is that we're going to hand out the Bitcoin Research Prize. We're still accepting nominations until the end of the month. The paper has to be in a peer-reviewed journal or conference and so on. It needs to be published recently, where this is the line, and it has to be somewhat relevant to Bitcoin and the Lightning Network. It doesn't need to be a Bitcoin paper, but it has to do something with the space, like no molecular biology or whatnot, but anything that is related. Please nominate your papers and send them off, and then it will be handed at the event. And another event that we're holding, it's called the Bitcoin Research Week. It's a small workshop. It's an invite only. If you think you should be there and we haven't contacted you, talk to us, drop us an email. So I hope to see you on November 22nd at the Bitcoin Research Day. I'm looking forward to seeing your papers nominated for the prize. We have an amazing committee that will go over it and choose the best one. Yeah, and talk to us. Thank you so much.
Hello, everyone. I'm Taro. I'm a PhD student from Carnegie Mellon University, and I'm excited to talk about our new research on a new type of denial of service attack that tries to exploit latency optimization in the Ethereum peer-to-peer network. So at this stage, we all know that latency matters in the blockchain peer-to-peer network. When the node receives transaction from the user, it will first validate the transaction and propagate it to the rest of the network. For the actors like MV bots and block builders who want to execute sandwich attacks or arbitrary transactions, they have the incentives to hear transactions faster than anyone else in the network to build a block or transaction bundles as quickly as possible. So oftentimes, they connect to the node from the centralized services that are known to be faster than the others. And in general, there are many ways to reduce latency. For example, you can deploy many nodes on a different location or maintain large connections to other nodes in the network. But the last thing you can exploit here is to skip the validation stage and by modifying the client and let the transaction go through without any checks. And indeed, we observe this behavior in the wild. So I'm not talking about like theoretical scenarios. However, because the node doesn't check the validity of the transaction, it will accept many invalid transactions to the network, which are supposed to be filtered out at the validation stage. So we as a researcher are interested in the security implication of this node modification, and we came up with a new type of denial of service attack where the attacker sends invalid transactions to this particular node, and it will incorrectly propagate to the rest of the network so that the original attack traffic gets amplified by 1,000 times. And on the one hand, we also try to quantify the economic benefits or economic values that you can generate from skipping the validation by reducing the latency so that we can ultimately answer the question on whether the risks associated with this attack actually outweigh the latency benefits. So we made this paper public a couple of days ago. So if you are interested in the answers to those questions, please scan this QR code and check this out. Thank you so much.
Awesome. Hi, everyone. My name is Mo Walji. I'm the founder of Derek.io. We're building a SocialFi platform for professionals, primarily starting with a job board. The idea is that we want to combine fragmented areas of identity across different areas of different chains into one place and allow that to have hiring managers to make informed decisions about as people are applying for a role. At the beginning, it's starting off as a job board. Allows, if you go in from a employer perspective, you should be able to get candidate information such as scoring on DeFi, NFT, DEX, and multi-chain usage. It shows how active you are currently. Aggregates things in one place, even things like DGen score, alongside with all your educational and experience in one place. We want to be able to give hiring managers the option to kind of look further in depth if they are looking for more crypto native people. And then further down the line, we're actually going to be opening up a reputational system and attestations, which allow people to start vouching reputation and kind of staking that towards recommending people for further things. If you do want to get in touch, or if you're looking for a job in the meantime, please check us out. Please take a picture of the slide. If you want to get in touch, that's my Telegram at the bottom at Incatera, or just simply give us a follow on Twitter at WeAreDerek. Thank you very much.
Perfect. So hi all, I'm Burak. This is our paper with Danning from Flashbots and Thomas Thierry from Ethereum Foundation. This is titled Who Wins Ethereum Block Building Auctions and Why? And as the title indicates, we want to understand how the successful block builders, the dominant builders today, win the auction, and also how they make profits, because as you can see in this chart, which shows profitability and the sizes indicate the market share of the builders, the size does not necessarily grow with profits. There are some builders who are not, who doesn't have that much market share but extremely profitable. So we want to understand, okay, how do they make profits and how do they win the auction? And we want to then get insights so that we can design better auctions in the future, which potentially preserves Ethereum censorship resistance properties. And our results show that the order flow diversity of the builders are positively correlated with their market share. This potentially is because if you have order flow coming from different providers, then you can be competitive in more auctions, whereas if you are dependent on a single provider, then potentially you are only competitive in less often auctions. We also show that builders who have potentially integrated searchers or exclusive order flow deals with providers are more profitable in general. The intuition here is that if you get order flow which the other builders don't really have access to, and this is strictly don't have access to, then you can keep profits while winning the auction, whereas builders who don't have such order flow, who are maybe dependent on common order flow, they can still win, but they have to subsidize. And then finally, we find a bunch of different features which are correlated with both earning profits, but also earning market share. And we actually converge to this chicken and egg problem that was also highlighted in previous works. That is, builders cannot profit from their blocks if they don't have distinguished order flow providers. But to get such providers, they need to have high market shares. And you can find the archive link or the paper archive version on this QR code, and the paper will be featured in AFT. And you can also just type in Vitalik got surprised by this chart on Google, and I think you will find the paper again. And that's going to be all. Thank you.
Hi everyone, my name is Yingqi. I'm a fourth-year PhD student at The Ohio State University. And I have a talk at 3 p.m. today. For now, I would like to introduce you Honeybee, decentralized peer sampling with verifiable random walks for blockchain data sharding. This paper was done by me and my PhD advisor, Professor Shailesh Bojavankar at Ohio State University. In a P2P network, nodes would like to sample other nodes randomly, and why would we care about this node sampling? There are a bunch of applications that need random node sampling. This include node discovery, data availability, and data sharding. You can consider data sharding part of data availability sampling, and also Byzantine tolerance and overlay construction. Basically, you cannot have a blockchain without these things. Therefore, it's safe to conclude that random node sampling is a very important part of network layer of blockchains. And now we introduce our work, Honeybee. Honeybee is the first effort to conduct P2P random node sampling with Byzantine-tolerant verification techniques for blockchains. And we use novel verifiable random walks and table consistency checks technology. And Honeybee is completely decentralized and robust against various attacks. From the evaluation perspective, Honeybee's node sampling quality is 4 to 63% better compared to state-of-the-art baseline algorithms. And most importantly, the Honeybee protocol is not only applicable to blockchains, it is also applicable to P2P node discovery and neighbor selection in general. As we already mentioned, in a P2P network, we want to sample nodes randomly from the entire network. How do we do that? We do that with random walks. And you probably want to ask, what if malicious node reroute your random walks? That's why we have verifiable random walk. In verifiable random walk, a node uses time-sensitive pseudo-random numbers to make sure that you are doing a genuine random walk. And you probably also want to ask, what if malicious node lie about their routing tables? And we already prevented malicious node from reroute your random walk. If we believe their lies about their routing tables, you can actually do a de facto rerouting. That's why we have table consistency checks. In this Honeybee protocol, nodes cross-check other routing tables randomly, and when we find a traitor, we slash them with fraud proofs. So here we have the evaluation result of Honeybee. As we can see here, Honeybee significantly outperforms the state-of-the-art baseline algorithms from the sampling quality. And thank you for your attention. Please check out our paper, Honeybee Decentralized Peer Sampling with Verifiable Random Walks for Blockchain Data Sharding.
Oops. Okay, so I'm Long Fei Qiu, and I'm presenting our recent work on Lido, which is about formally verifying the safety and liveness of consensus protocols. So we know that consensus algorithms lie at the heart of blockchains, but they are also very difficult to implement completely correctly. And if we look at the bugs that occur in consensus algorithms in the wild, we can see that there are mainly two kinds of reasons that the implementation can be incorrect. First, that your algorithm might itself be incorrect. And second, even if your algorithm is correct, your implementation might deviate from your spec, so it becomes buggy. So it's not enough that we have paper proofs of consensus algorithms. We need formal guarantees that can connect your implementation all the way to an abstract spec, which in most cases is the SMR, state machine replication. Now, formal verification, we know that it has a bad reputation in the industry. People consider this kind of work inefficient, and they consider our implementations as toys, mostly because first, most implications need very ideal assumptions, and they are also very difficult to reuse because you must reprove all the invariants as soon as you modify your implementation. And this means you cannot incorporate the optimizations that are useful in the industry. Now, our belief is that all these difficulties can be overcome by using refinement, which is a proof technique where you first build the safety proof of a simple unoptimized system or abstract system, and then you prove that your optimized optimization simulates the behavior of a simple system. So based on this idea, we introduced a model called Lido, which is an abstract framework for a leader and round-based consensus algorithms. And using our approach, you can structure the formal proof of your protocol as a sequence of refinements, as shown here, where on the top level you have SMR, and on the bottom layer you have your network implementation. And this can be at first be an unoptimized version, and later you show that an optimized version simulates your unoptimized implementation. So to summarize our achievements, we already achieved this formal safety and liveness proof for Jotian, which is a very recent consensus protocol. And we verified both unpipelined and pipelined versions of it. And we established both safety and liveness. It's the first formal liveness proof for a pipelined consensus algorithm. And the implementation can be extracted to a OCaml executable. And also, we are in the middle of extending this work to cover the more recent algorithms, such as DAG protocols and BFT protocols. That's all. Thank you.
Hi, everyone. I don't have a presentation, so I'm going to make it short. My name is Pak. I'm a co-founder at Moti, which is an identity protocol where we focus on creating utilization and monetization for self-sovereign identity. Each user generate about 150 gigabytes of data a day, making California $5 billion a day. But the users don't actually make anything. So our solution is that we have built a deepened network that is centered on identity that allows people to basically bind all of their Web 2 and Web 3 accounts across the internet into their DID and enable them to run computation using their private credentials in a secure way. And so what we want to do now is to basically use this structure to build a social graph based on peer-to-peer credentials, verifiable credentials, that enables us to basically create a new age of digital connections. I would love to talk to any experts in identity, someone that is very passionate in it, outside, perhaps over a coffee. And that's it. Thank you very much, and have a good time.
Okay, I have a good news and also a bad news. My talk is going to be funny, and also the bad news is I need 1 extra minute. Okay, so I have I have a cryptography background. I want to mention that cryptocurrencies are not cryptography. Cryptography is a wider range of study that we consider multiple stuff, and cryptocurrency are some subset of this word. So many people, I talk outside during this conference, and they think that we are the security guard of digital world, okay? I believe that we are not. We are just chefs and farmers in this world. Why? Because I believe that there is a close relation between human food chain and also cryptography chain. In the human food chain, we have the primary resources, light, water, and soil. They go to herbs and also algae and vegetables. And primary producers like fish, cows, and sheep are going to give us the protein. Essentially, they are going to be mixed to have delicious food for the consumers and the people that they are going to the restaurant. On the other side, we also have pure science, math, and physics. From them, we extract some hardness assumptions, D-log isogeny base, lattice base, and so on. And then essentially we go to cryptographical primitives, okay? By mixing some cryptographical primitives, we will have cryptographical protocols. Bitcoin, Ethereum, and some other cryptocurrencies are one protocol, which is a mix of multiple ingredients. And essentially, we are going to serve them. In the human food chain, we have multiple ingredients, potato and onion. It's also the same in cryptography. We have multiple types of digital signatures, okay? Digital signatures are potato in our world. BLS, RSA, Schnorr, and so on. What are the onions? The onions, in my opinion, are zero-knowledge proof systems. One hint, starch are good for frying. So TLS is a mix of potato and oil, a high-quality oil. We already said that potatoes are digital signatures in our world. What about the oils? The oils are key exchange protocols. Choose your perfect key exchange protocol, choose your perfect signature, and essentially you have such a recipe for TLS. However, we might actually go, instead of having a French fries, we might actually have a Persian fries. Now you have to add saffron to French fries. In this case, you have to add BGV to the TLS, which is a FHE scheme, and is super expensive. So I just want to wrap up here that many people are working on ZK-TLS. ZK-TLS is going to be a ring onion next to the fries. Dan told me that make it more healthy. Now it's a salad next to it. Thank you so much.
And it's almost working. Okay, so I'm Csaba Király from the Codex research team. We are working on a decentralized storage network, focusing on data durability. We also work with the research team with the Ethereum Foundation on scaling L1 and also with the client teams. So actually all the people that you see here, Leo, Dimitri, me, are here. If you want to talk about these topics, come to us. Or, as an alternative, there is this material that I wanted to show you. Unfortunately, I don't have a write-up on this one, just the ECC talk. So in this talk, I was introducing data-based sampling. That's less interesting, I think, for those who know it. But there is also PIRDAS. PIRDAS is the next iteration that will be implementing in the next hard fork of Ethereum. So there's an introduction to that. And even more interestingly, I think, the techniques that we are introducing to go even beyond that, to target 32 megabyte blocks, or more formally data related space related to blocks every 12 seconds. So, and finally, I was also giving a broader perspective related to data, decentralized storage networks and data arbitrary layers. So if you are interested in these topics, come talk to us, look at this one, or look at this one. This is an East Research write-up on FURDAS. So FURDAS is kind of the summary of techniques, and it's a bunch of techniques that we were developing to get to the 32 megabyte or beyond or near. So to scale layer 1, 6 techniques there, or 7. Lossidas is an interesting one, which is focusing on not having that many false negatives, which is a less known huge problem with data sampling, availability amplification, topic routing, and then networking techniques, more traditional peer-to-peer networking techniques, which make it hopefully work for larger block sizes. So if you are interested in these topics, come talk to us. We are all here at SBC. Thank you.
Hi, everyone. My name is Eric Forst. I'm the co-founder and CEO of Bloxy. We're a Web3 data index for AI model building. Started our company 2 years ago as a Web3 CRM based on the idea that the wallet is the new cookie. That allowed us to build a data index that correlates off-chain data to a wallet address. As the NFT market went away, we found a new use case for our data index. And we're now powering a new BitTensor subnet, number 45, that just went live last week. And they're using our data index to build a wallet risk assessment model that's useful for payment apps, wallets, DeFi apps. We just finished the first cohort of the Crypto Oracle Collective AI Web3 Accelerator, where we received 200,000 in grants from the Manifest Network. I'd love to talk to anyone who has an L1, L2, or L3 that would like a data index optimized for AI. Come find me. Love to talk to you. Thank you.
Is it showing up? Any technical guys here? Okay.
Hello, I'm happy to have no technical difficulties because I did not prepare a presentation. Apologies for that. My name is Luke Parker, also known online as Kayaba. I am a researcher for the Monero project, and I have my own work, but that's not what I'm here to talk about today. The Monero project is currently working on replacing ring signatures, which have a linear prover and linear verification time, with a Merkle CK proof of some output existing in a Merkle tree to offer full sender privacy instead of sender privacy within a subset of the outputs on chain. As part of that, we've moved forward a few pieces of cryptography because we're solely using a trustless set of cryptography. And when you need trustless set of proofs, you have poor performance compared to trusted setup options, so we've really had to optimize our verifiers and our circuits to be as small as possible. And with that, we look to Liam Egan's work in 2022 on using divisors and the function fields of elliptic curves in order to prove sums of points. And the end point of all of this is that we have funded the security proofs and are working on the implementation of deployment of proofs of discrete logarithms in a zero-knowledge circuit with just 7 multiplicative constraints over R1CS, which is a 72 times improvement from the industry standard of using double and add over 256 points. If anyone wants to talk about that, I'm available too. I just thought it was worth sharing, this being a cryptography conference and all. Thank you for your time.
Awesome. Hello, everyone. My name is Sung Han, a student from University of Illinois. I assume all the folks in the conference here has a smartphone, and maybe some of you are staring at this right now. If you misbehave with your phone by downloading some suspicious applications, you expose the phone under the risk of information leakage as well as intentional intervene. Probably most of you have crypto wallets, and guess what? The crypto assets are in danger. So I have thought of moving all the wallets operation into the mobile TE. The workflow is simple. You have a request, sending to the app. You relate to the precompiled TE, and internally it verifies the request and performs private application operations like signing. All the necessary information on the chain will be obtained through observer nodes with attestation. Since TE has the highest priority inside the phone, no other apps can intervene in the operation or spy on that. The only approachable attack is to steal your phone and to break it. So the above problem is solved. So I will show a brief draft timeline for the application. But is that the end story for the mobile TE? I don't think so. So back to the old time, so where the Apollo 11 can achieve its mission with only 4 kilobytes of RAM and only 70 kilobytes of its ROM. So definitely with mobile TE, we have more use cases. And I'm looking forward to collaborate with some of you guys in the conference. Some of the ideas I had includes decentralized ML, secure web browsing, maybe distributed VDF using the small devices crowdsourcing, and etc. I will leave my contact at the end. And finally, is that still the end? I don't think so. So right now we build our trust on top of hardware, on top of manufacturer, and also on top of the developers. So I would like to delegate this to the math, which by replacing the components with the current cryptographic protocols, definitely with efficiency. And thanks for listening, and this is my contact.
Hello, everybody. I'm Drew Austin. No slides, just wanted to quickly introduce myself. I'm the founder and managing partner at Redbeard Ventures and Denari Labs. So just to tell you a little bit about us, there's a lot of really incredible builders here. We're one of the more active investors in the blockchain space. We've invested in over 200 plus companies across a wide range of sectors and across a wide range of stacks. A little bit about our ecosystem. We have an AngelList syndicate, which has now about 4,500 accredited investors in. You guys are all welcome to check it out. We have amazing deals that we've distributed through that network. We kind of use that as both a marketing engine and fundraising engine for a lot of really interesting and creative companies in the space. We then raised our first managed capital fund, which is, again, a blockchain-focused venture capital fund, Redbeard Ventures Fund 1. We're now kicking off fundraising for Redbeard Ventures Fund 2. And then we also, about a year and a half ago, started Denari Labs. Denari Labs is a tokenomics consulting and accelerator firm. So, you know, we kind of came across two different gaps that were happening across the majority of our investments. One was that most of the companies specialize in one key area of their business and value proposition, but understanding how to launch a token, how to go to market with a token, understanding sinks, faucets, risk mitigation, exchanges, market makers, all of that was really a black box and a kind of a a gray area for people. So we come in and built out an expert team to support the companies in that area. The other part is like developer adoption is key for most of the infrastructure investments that we are investing in. So we partner with a lot of these ecosystems and invest in companies building on their stack, evangelize the stack, and we built out a whole team to support that. So I'll be out in the hallway. Feel free to come by. I thought this would be a better way to just let everyone know that, if you some great builders here, and we're actively investing and want to support this ecosystem in whatever way possible. So thanks for having us. And you can find me on Twitter at Drew Austin, and on email, if you want to email, it's drew@redbeard.ventures.
Hello, everyone. My name is Tahir Mahmood. This is my LinkedIn profile. I'll just keep it up here for 2 seconds. You can contact me on that. That's probably the easiest place. I know we all use Telegram, but anyway, let me start. So I think a very lucky stage. We, as Kernel, I'm the co-founder and CTO, are literally about to come out of stealth, and the project is named Kernel. Basically, what we do is we're allowing a transaction, then normally that you have a transaction that goes to a node to be able to do much more than it's ever been able to do. And that's what Kernel is all about. We expect basically to be able to have a new paradigm where a blockchain node in itself is able to do much more than what it does today. So just imagine a transaction being transmitted into a node, and instead of going to the local pool, mempool, being propagated out, that it could actually execute so many other things. And that's what we call kernels. Those kernels, limitless functions, they can be on-chain, off-chain. So we utilize technologies like account abstraction, Web2, open API specifications with GPRS, all the other sort of stuff that you can imagine. It's quite strange how many technologies we use. What I'm going to get down to is the use cases that we have is that imagine you're able to transmit a transaction, do KYT compliance, KYC, the transaction goes on, proof of provenance, that all that execution took place, so you actually know that that transaction is valid and all the proofs are there. What I want to get down to is it's all based around osmotic computing, a lot of this technology that we built. I can go into the use cases, but this diagram probably gives the best example of what we do. Imagine having it that every smart contract function on every chain is accessible to you from the initiating chain. It's a very simple concept, but imagine the whole economy being able to be accessible from one place. I'll just move into that, the architecture, as I'm the technical guy. It's very simple. We have modified a Geth node. That's where we're at the moment to be able to achieve and do all these great things. We'll be able to support all EVM and non-EVM chains in the future. There is a token economy that goes with it. It's a two-sided marketplace. It means people who have got all these smart contracts, which are, I call it, on sort of a very chains which are not making much activity, to be able to bring all of that to other chains. So anyway, I'll leave you today with, we're looking for builders to build on our economy and build on what we're doing. We're literally at the stage of coming out of stealth in the next 2 weeks. Thank you very much.
Good morning. My name is Derek. I am from Nartella Network. We're building what we call extensible blockchain. Let's just dive into the technical details. So pretty much what we're doing is called the EVM++. What it means is that we're using parallel EVM and elastic block space to boost the scalability. And on the other hand, which is where the things get interesting, we are actually throwing a extension layer in between the dApp layer and the base layer, and in which there lives what we call aspect, or actually the virtual operating environment that allows people to customize some conditions for the smart contracts to be met before they can be executed. That's what we call aspect programming. And immediately after that, if you want to check more about the technical details, you're more than welcome to log on to the official website and check out the white paper over here. And I should probably also mention that we're actually in the middle of the incentivized testnet. So obviously, we're looking for more people more infra builders to build with us on these customizable structure, and also more DApp partners to cooperate with us on the incentivized testnet as well. I should probably mention that last week we just surpassed a 1 million user on the incentivized testnet, which is obviously a huge milestone. Very happy for it. If you want to get more of the user base, please, you can either send a message to our Twitter, and also you can find me anywhere in this venue. And happy to talk to you. Thank you.
Hello, everyone. I'm Sachin. I'm one of the co-founders at Bionomy. And Bionomy is a infrastructure company that's focusing on solving the user experience on blockchains, basically. So we are a B2B platform. How we are doing it? We are providing a full stack account abstraction solution for developers building an Ethereum ecosystem, all the EVM chains. And we provide like smart account functionality, paymaster and bundlers. So if you're familiar with ERC 4337, you would be knowing these terms. But the end result of these technical terms is the user experience, basically. As a user, you want to use blockchain applications that are easy to use, that have less friction during onboarding. You want to get onboarded to application as quickly as possible without downloading a wallet. So things like social logins, where you just use email ID to log into a decentralized application, get a blockchain account, and that account will be a smart account. And then after that, you want to interact with the application and doing on-chain transactions. So when you do transactions, you deal with gas fees. And when you do cross-chain transaction, there are like a lot of complexity over there. So we are trying to solve the user experience when you interact with blockchains also. So the functionality like paymasters like helps application developers sponsor those gas fees on behalf of the users, so they can just go to the application and just do click of a button and the transaction happens behind the scenes, and the user don't have to pay for any gas. User don't even have to know what the gas is. So these kind of UX we want to enable on the applications, and this technology actually allows us to do that. There is this new standard I want to talk about, like ERC 7579. That's a standard for building modular, smart account, and our smart account is based on that. And the cool part is that it's open and it's modular, where if you want to extend the functionality of your smart account, let's say you want to add like a multi-sig functionality or spending limits or any other feature on your account, you can do it via modules, and anyone can build these modules, if you're following this ERC. And anyone who wanna know like what's going on in account abstraction space, like what kind of traction there is, you can visit this site bundlebear.com, and you can see like there are 12 million smart accounts that have been deployed across multiple EVM chains. Total 46 million user ops have been done. And this recent spike you are seeing here, that's because of the Coinbase smart account that is like gaining a lot of traction like lately. And one last thing I want to mention here, there is this EIP 7702 that's like coming in next Ethereum upgrade, the Pectra. And it will actually allow EOA to have like a smart account like functionality. So I'm really looking forward to it. But yeah, anyone who want to talk about UX, I'd love to talk about that. And thank you.
All right. Can someone take a picture of me so that I can show my professor about this? Thank you. Is it working? It's showing up on the screen here, but not. Oh, there. There we go. Okay, hi everyone. I'm Suyan from University of Wisconsin-Madison. I work with professors Ramsey and Andre Apshiduso. If you know them, they are experts in the storage system in the crash failure world, but we're relatively new to the blockchain world. So kind of like as a first step into a new field, we want to understand what's already out there in the wild. But that's a little bit tricky with blockchain systems because, well, the implementations out there are production code, and we only want to know how fast a plane can fly for when this is what we see in production. The second problem we really face is that we want to understand its performance at the scale in the wild, which can easily go over thousands of nodes, but we don't have that many machines around because we're just research groups. So what we're gonna do? Well, for the first problem, we want to know how to, we really have to put those blockchain systems under the same framework. And hopefully this framework can be modularized so that we can easily identify the problems in the blockchain system. And also it should be generic enough so that we can accommodate most of the blockchain systems in the wild. And this is what we came up with. At a high level, I'm not going to go too detailed about this, but this is what I'm showing here is this pipeline for maintaining the memory pool. And once you have the memory pool, this is kind of like a pipeline to manage transactions into blocks and get the blocks committed. Several things I want to point out about this model. This is a stage event-driven architecture, and seed architecture is well known for its ability to identify bottlenecks. And out of the decent number of blockchain systems we have been studying for, it fits pretty well with all of them. So that leaves us the second problem. How do we test its performance at large scale when we don't have that many machines? The answer to that, there's a 2019 paper in FAST conference that kind of sheds light to the solution to this problem, and it says that the key to computation is not really the intermediate results, but just the execution time and the eventual output. So what that says is that instead of running the actual computation, actual disk I/O that can be really expensive, we can just put the program into sleep and returns the result we expect to have. That way, we are able to save a huge amount of computation and disk bandwidth, and that allows us to pack multiple validators onto a single physical machine. So now we end up with this. We have these validators talking to an underlying virtualized network layer, which we will refer to as mailbox. And I'm running out of time. So the last problem we have is network I/O, which is really not a problem because the validator nodes usually have like a much lower bandwidth than data center network. I also got some results, but for the sake of time, I'm just going to skip it over. If you are interested or you have any feedback on our project, please do let me know. Thank you.
Hi. I just want to talk about this LLVM bug that appeared a few weeks ago. This is a convoluted function which essentially just computes 4 minus x, but which accidentally gets compiled to only return 4. And so this is a bit of a problem when you have a lot of ZKVMs using LLVM to compile code down to ZKVM instructions. And so this highlights a problem in the whole stack where we don't really know, we can't be sure that the code that we're compiling down to ZKVMs is actually like the code that we're intending to run and essentially prove. And so, well, I get that this is a very convoluted example and that in most cases, you can trust the compiler to actually do the right thing and give you the correct result. It also highlights that there's essentially a gap in how you can trust that what you're proving is actually what you intend to prove right. And so nobody could go around and audit all of LLVM or like actually make sure that, look at the assembly and make sure that everything is running. And I know that there's also a lot of projects which are working on like verifiable compilation, et cetera, and like using formal verification methods. But this is something we need to be aware of, and also to be able to like have defense in depth methods, such as TEs, to make sure that that we can handle these kind of failure modes. I work for Argument, formerly known as Lark, and we believe that when you're building these systems, you have to be honest with what you're trusting in your whole stack, down from the code you're writing to the compilation phase to the proving phase. And so we're trying to push the limits of like what we can do with ZKVMs by building a much simpler language which is based on functional reduction, and we're looking into building verifiable computation as a ground up, so that the whole system is simple, easy, and auditable. So thank you. Please check us out.